Hello, this is Mahan Rathidia. In this portion of the book on liquid formulation, we cover emulsion formulations using integrated approach to formulation development. In this section, module 15, we focus on equipment and processes. Equipment and processes are interrelated. If either of them fails to perform, then an entire product fails. Reader is requested to review Module 7 and Module 11 for details of equipment, density, and mixing tank capacity calculation. We will not look at that in detail in this module. Reader is requested to allow sufficient time for manufacturing process submodule video as emulsion formulations are complex. We will not go into details of manufacturing guideline, except mention here that FDA guidelines require description of each production step, actual operating conditions, and equipment utilized, including point of sampling for in-process control. We will look at that in second submodule. Let's refresh what are the energy required in formulation of emulsions. Formulation of emulsion requires two separate immiscible phases. Generally, we'll refer to them as oil and water. The globule formation requires shear energy, that is mixing, and optionally thermal or heat energy. Shear energy results into deformation of dispersed phase into droplets. So let's take oil and water as an emulsion, and as we apply shear, dispersion of one of the phases, in this case oil droplets formation into water phase, or water droplet into oil phase. Continuous phase flow due to shear energy results into the shape of the globules. Thermal energy increases the mobility of the flow of both phases. Equipment that we need is capable of providing shear energy by mixing and thermal energy by heating. Emulsion stabilization, that requires lowering interfacial energy. Surfactants orientation on globule lowers the surface tension at the interface during mixing. Dispersed globule formation is protected by emulsifier orientation. Oil is dispersed phase and water is shown as a continuous phase. The emulsifier will orient so that the polar head faces the water phase. Double emulsion energy. Double emulsions are emulsion within an emulsion. That means dispersed phase is a globule, stable primary or inner emulsion in a separate continuous phase. Example here is water, oil and water, W1, O, W2, shell phase designated by the middle letter, in this example O. This is the primary emulsion. And primary emulsion contains core phase, shell phase. Shell phase is not miscible in both inner core and the continuous phase of double emulsion. Primary emulsion, the interfacial energy is provided by the surfactants orientation. It requires high shear energy to produce submicron emulsion and high thermal energy. Double emulsion, as shown here, it is protected by the emulsifier. Outer emulsifier do not migrate into the primary emulsion. Shear energy is low to prevent breaking down of a primary emulsion. Thermal energy is also low. Let's look at high-level processing. In this case, we're looking at monoemulsion, emulsion that contains two phases, oil phase and an aqueous phase. Oil phase, dissolve all the oil components, including emulsifiers, and mix to form a single oil phase. Temperature can be 75 to 85 degrees. Aqueous phase, dissolve and mix all the aqueous component to form a solution, and temperature can range from 75 to 85 degrees. Emulsifiers are added either in oil phase or aqueous phase, depending on essential piece. Active components are dissolved in one of the phases, again, depending on the drug solubility and its infectional use. Emulsification. Dispersed phase is added to the continuous phase with high shear mixing. This will preferentially form dispersed phase globule. Homogenization step is added using a homogenizer to achieve target globule size. In some cases, suspenoids and volatile ingredients are added, such as flavors, mica, after the emulsion is formed. It's important to emphasize that process used in the development of the product in laboratory should be similar to commercial processes. Let's look at how laboratory batches are made using small mixers. What you will see in a couple of videos is we start mixing continuous phase, and depending on the product, we'll use a higher temperature, and the dispersed phase is added at a slow rate to the continuous phase. And we'll adjust the mixing speed manually to maintain or as viscosity changes. And submicron size emulsions require homogenization using high pressure homogenizer. In double emulsion, primary emulsion is prepared and is used within 4 hours of manufacturing. That is, it is freshly prepared primary emulsion. So let's look at laboratory manufacturing of siloxane-based emulsion. This is a small beaker and a mixer. And we'll manually add water. And this is typical of laboratory procedure. Mixing, even at lab scale, for siloxane emulsion is very important. Let's look at the second video. You will see use of spatulas, high shear mixing, manually addition of the materials. This is typical of laboratory procedures. So using high shear mixtures, one can get droplet size of 2 to 5 microns. Let's look at equipment at commercial scale. This is one of the processing equipment. Has a scraper blades that scrapes the surface of the vessel. It has a mixing blades, as shown here, that has a counter flow, so for efficient mixing. And at the bottom here, it shows high shear mixer. Let's look at video on manufacturing. Case capacities are mentioned in kilos of water. Water phase vehicle. If the materials are soluble, it's acceptable to have propeller type mixing. Wax phase or oil phase has a blade mixing. Main mixer has a complex mixing system to emulsify materials. 300 kilos would be a manufacturing size. Emulsions require homogenization, and we'll look at online homogenization and high pressure homogenizers. Droplet size of 2 to 5 micron can be achieved by online homogenizer. Online homogenizer is connected to the main vessel. It's a rotor stator. The material is homogenized and particle size is reduced. In some cases, we need submicron size, such as nanoemulsions, and it requires high pressure homogenizers. High pressure homogenizer has an in-feed of micron size material, and there's a small gap where it impacts, and much smaller particles are generated right here. These are the key equipment that are used for emulsification process. Reader is requested to review modules 7 and 11 for solution or single phase manufacturing. Let's look at two emerging technologies. One is a nano emulsion without mechanical energy. This is at laboratory scale. Oil and water form an emulsion, but it will not be stable. It will break without emulsifier. Oil phase is added to a disc, and water then is condensed over the oil phase. This then produces emulsion. An actual emulsion is translucent. Let's look at double emulsion with a special technique. A mono inner emulsion is encapsulated in a continuous phase. Core phase, shell phase, and a continuous phase are sequentially added. Water with a black ink, emulsifier with oil phase, and water with vim. Shell phase is prepared first, followed by core phase and continuous phase. The microscope is attached. Double emulsion particles are shown here.